Hi guys, welcome back to the channel. In this video we are going to see applications of shift register. So let's get started. So there are many applications of the shift register. In this video we are going to discuss some. So let us start with the first one. The first one is generating a time delay. So we already know about the serial in serial out type of shift register. In the previous videos we have already discussed that it requires 4 clock cycles to take all the bits from the output side, and we also understood from the timing diagram analysis. So you can see, so after all 4 clock cycles only again the whole thing would be started repeating. If you send 1011, it will be going to produce again and again if you connect back. Means what is meant by that, after 4 clock cycles the sequence would be generating again and again. So that is that we can say simply the time delay, the generation 4 clock delay for the 4 bit. For the 4 bit shift register, we have to encounter 4 clock pulses or 4 clock cycles delay. For the n bit shift register, we are going to have the n clock cycles delay. So we can use this delay wherever we want. So the next and foremost very important application of the shift registers is serial to parallel and parallel to serial data conversion. So let us understand what is meant by that. So in generally our computers use the data in parallel mode so that it can increase its speed. So at a time more things or more lines working, it might reduce the time and reduce the time delay also. In 1 clock cycle only the all parallel delay will be completed, or the output we can generate in 1 clock cycle if you use in the computers. So but what if you want to send the data to another device? So we have to send only in the serial format, because if there is a huge gap between both of the devices, we cannot have the 64 lines. If you are using the 64-bit machine, it's very huge complex, and it might have the more costly, more complex to design that 64-bit line all over the way to the other device. So we are going to use the serial format to send all the data that the computer has been produced. So to avoid the sending of parallel data in 64-bit machine, we cannot have the 64 parallel lines to send the data. So we are going to use the converters for this conversion. Machines use the parallel data, no problem. So the parallel data would be sent to the shift register. The shift register would convert that data to the serially. So the serial data would be converted to our required devices. So that is the main use of the shift registers. Not only that, the vice versa is also possible. Suppose a serial data is coming towards our computer, but our computers can access only the parallel data. So there we can have the 4-bit shift register, so that can convert serial data to parallel data, so that our computers can use efficiently the parallel data fastly. So commonly in the market, this is the main thing that used in the serial to parallel and parallel to serial data conversion, that is UART communication. So the full form of UART is Universal Asynchronous Receiver Transmitter. So the next application is the sequence detection. So assume we have a serial input that is in the format 01011 like that. We have some sequence that is sending to the 4-bit shift register, and we are going to find out is the sequence is present in that sequence or not, in the random sequence, that is 1011. We are going to find out how many times in the random sequence we have been getting the 1011 as our one of the sequence. This can be achieved with the help of sequence detection by shift register. So let's see how to do that. So this is the circuit for sequence detection of 1011. So basically already you should have the memory that what we have to detect. So we are going to detect 1011, how many times it is occurring. For that we are going to join each and every one with the memory, that is the first flip-flop with the first memory, first shift register with the XNOR gate. Like that all the 4 flip-flops should be joining with the other 4 memory elements. So each and every joined with the XNOR gate. So we already know when XNOR gate output is 1, when is that? When both the inputs are same. So when both the inputs are same, the XNOR output would be the same. So if all the 4 XNOR outputs are 1, then yes would be 1, because that is AND gate, right? In that way we are going to find out if that sequence, the serial in sequence when 1011 is exactly gone into the 4 flip-flops, then that and memory also will be matched. So both are matched, then the inputs are same for the XNOR gate. So inputs are same, the outputs would also be the same for the XNOR gate. So finally S would be 1, then we can blow the bulb and we can know about that this sequence is matched with our sequence. So that many times our required thing is sequence is detected. The next application is the ring counter and Johnson counter. This is the preview or the circuit diagram of the ring counter and Johnson counter. This is somewhat similar to the shift register. Basically, it is the extension of shift register. So just joining, that's it. So we have already covered these two videos in the playlist only. Please check it the playlist. If you know, just see the circuits. It's almost similar to the shift register. So if you want to exactly represent in the form of shift register, so the four boxes are indicated the four flip-flops of shift register. So this is in the format of shift register. So basically you are giving the output as feedback to the input again, that is Q3 again giving to Q0. So that is the ring counter and that is the shift counter, means shift register format. So if you want to represent the Johnson counter, the same thing, that we are going to take the reverse, the feedback, the inverted one or the complemented one. That shows our Johnson counter. So you can also see there, we are giving the serial input and we are getting the serial output, but we are taking the feedback. That's the change, that's it. So if you want to analyze with the help of the truth tables also, these are the truth tables for the ring counter and Johnson counter. So basically if you see how the movement of one happening in the ring counter, you can also observe that. So basically first of all you are taking 1 0 1 0 0 in the ring counter as Q0 as 1, remaining things as 0. So the shift is happening of 1. Again it is coming to the original position. In the Johnson counter also, if you can also observe that how the shift is happening. And one more important thing, in the Johnson counter, the number of flip-flops into 2 gives our number of states. So 4 flip-flops we have because 4 boxes into 2, total 8 states we are going to have, or 8 transitions we are going to have in the Johnson counter, because we have inverted, not gate here. The next application of the shift registers is the sequence generation. So you can also observe here the same thing I have took here, that is serial in, serial out. If you observe clearly, I took the sequence 1011. So this sequence will be generally repeated every time, that is 1011, 1011, 1011. So this is the sequence will be repeating always. So with this we can confirm with the shift register, whatever may be the sequence repeatedly we want, we can generate with the help of shift register. If you use more number of shift register, means more flip-flops in the shift register, you can use the repeating mode much more larger. If you want example, this is the example. Here I took 8 flip-flops in the shift register, means each box represent 1 flip-flop. So you can observe the sequence is again repeating the same. 8 bit means 1 0, 4 ones and 00. Again the same sequence is repeating. If you want anything should be repeated that many times, that flip-flops you can take and you can have the shift register. And you can generate whatever sequence you want, you can pass into inputs and you can get the same thing in the output as well. The next application is very important. This is PRBS. So PRBS means pseudo random binary generation. So with the help of the circuit, with the help of any logic or combinational circuit to the shift register, we can generate some random binary generation, random things or random sequence I can say. So you can observe that in the 4-bit shift register I took in the position of the Q1, means the output Q1 and Q0 is XORed and given as feedback to the D3 again. So this generates our random sequence. So let's see how the random sequence is generated. Let's understand. So the same thing that I have represented with the help of the block diagram. So you can see each block represent each flip-flop, and I have started the thing with the help of all 4 ones, or initialize with all flip-flop outputs as 1 1 1. And the XOR operation would be the same. The Q1 and Q0 is XORed and again given feedback to the D3 again. Now we are going to observe the truth table so that we can understand how this is the random sequence. Okay, like that. So the expression is for the Q3 is Q1 XOR Q0. So in the general way we have started with all ones and we are going to perform each time Q3 is equals to Q1 XOR Q0, and we are going to proceed the movement of the shift register, and we are going to have all possible combinations. As we are having 4-bit shift register, we are going to have some 15. For this example, we are going to have the 15 times change is happening. So if you observe, the first one is 1, all ones are started. The next one is the Q1 XOR Q0. So 1 XOR 1 is 0. So Q3 is 0 and remaining things would be the same. Like that you are going to fill all the 15 combinations. So 15 here 0, 1, 2, 3, like that means it is not represent to the min terms. So that represents the clock cycle. So total 15, after 15 clock cycles, it is again going to come to the same state. So I can simply say we have required 15 clock cycles to come back to original state. But remember, those are not min terms. As this is the serial in, serial output, we are going to take the output from Q0. So if you observe the Q0 column, that is some random sequence. It is not just 0 1 0 1, not like normal truth table. because we have XOR operation over there. So this random sequence is generated, that is known as PRBS, pseudo random binary generation. You can see that all are different, all the 15 bits are all the 16 bits are different. So that is known as length. So length is for this 4-bit shift register with the PRBS is 15 random sequence. If you have the n-bit shift register, you are going to have the length as 2 power n minus 1, some random sequence length, that is. If you take the output from Q0, it's not confirmed that if you are using 4-bit shift register, we are always getting up with only the 16 states or 15 states. It's not like that. It depending on the position. So if you observe this situation, I have connected the second input of the XOR gate to the Q2, not Q1. So it is different from the previous state. Exactly. The Q3 is now Q2 XOR Q0. In this state, we are going to just end up with only 6 states or 6 clock cycles is needed to again retain or regain our previous state or again getting the same state as we are starting with. So suppose I have started with 0011. So get the same state 0011, I need total 6 states. You have the Q3 expression, so you can go through Q3 and you can have the Q2, Q1, Q0 directly. You can have the changes like that, and you are going to shift rightward. So performing these expressions and finding always the Q3, filling the truth table, you are going to end up with 6 states, and the length will also have the 6 states. So length depends upon position also, and which state you are going to start. So as I started with 0011, we are ending up with 6 states. So suppose you are starting with 0000, you might get some other thing like that. Like this, all situations will be possible. With the help of the shift registers, we can perform the arithmetic operations like addition, multiplication, division. So using shifting property of the shift register, it is possible to multiply or divide the numbers with the help of power of 2. Now we are going to understand that only. Here we will understand how the multiplication and division happens with the help of shift register by shifting the digits. First of all, I will explain the left shift. So one thing, with the help of left shift, we can perform the multiplication in the power of 2. So how that can happen, let's see. So I took the 6-bit shift register, that is starting with 000101. So I hope you know 101 in the binary and 5 in the decimal. And to the right word, that is grounded. So now you are going to insert from the right side as 00 by 1. So let's see how to do that. So if you start inserting 0 1 by 1 to the right side, so basically starting going to the left side, you are ending up with getting 1010. So that is 10 in decimal. You can observe in the previous we had 5. So 5 into 2 gives our 1, means what? 10. The same thing that again you are going to perform. Then one more 0 you are going to insert from the right side. That gives again one left shift. And basically now that is 10100. That is basically 20 in decimal. So we can have the previously starting with 5. We are going to multiply with 5 into 2 power 2. That gives 20 again. And again one more left shift if you perform, or if you insert 0 to the right word, then you can end up with 101000. So that is in decimal, that is 40. So you can observe we have started with 5 and 5 into 2 cube, that gives 40. So I hope you can observe the sequence. So 5 into 2 power 1, 5 into 2 square, 5 into 2 cube, 5 into 2 power 4, like that it is going to have some sequence. So basically the number or the power represents the number of left shifts. So as you are multiplying in the 2 powers, that is in the multiplication by left shifting. We can simply say with the help of left shift we can perform multiplication operations simply. In the same way, with the help of right shift we can have the division. So I am starting with the 52, that we are going to have the 0 or the ground in the left side. So left side means basically 0. We are going to move towards right, or we are going to insert zeros towards the left side. So that is the thing. Where there is ground, that side you are going to insert zeros. So 110100, that is 52 in decimal. Now if you observe the first right shift or 0 is inserted towards the left side, if you see that is 11010, that is basically in decimal 26. So 52 divided by 2 power 1. And again one more right shift, you are going to end up with 1101, that is 13. 52 divided by 2 square gives 13 again. I hope again you can see the format, how the given number is divided with the 2 powers when we are moving to right shift, or when we are performing the right shift or moving towards the right. Finally, I end up with this situation. You can also move further also, that is your wish, but I hope you understood this one, because after one more digit also, that is 52 divided by 2 cube, That is basically 6 point something you will get, but unfortunately in this right shift you are going to have just the decimal, not the fraction you are going to get. So this is the thing that you are going to divide in the two powers with the help of right shift. Right shift register, you can perform all these arithmetic operations. Not only that, you can perform multiplication and division as well. Sorry, addition and subtraction as well. I hope you understood this video. Thanks for watching up to now.